April 27, 1945. The volcanic ridges of northern Okinawa. A Japanese soldier crouched deep within a reinforced concrete bunker, 75 feet below the surface, connected to his comrades through 11 miles of hand-carved tunnels. Sergeant Takeshi Yamada had survived the opening bombardments of the American invasion with confidence. His position was impregnable, built to withstand anything the enemy could throw at it. For 26 days, he had watched American shells slam into the hillsides around him, exploding harmlessly against rock and earth. The explosions sent tremors through the tunnels, yes, but they posed no real threat. His commanders had been right. The underground fortress would protect them. When artillery struck the ground, most of its energy and shrapnel blasted upward and outward. Down here, in these depths, they were untouchable. Then, without warning, the nature of the bombardment changed. Yamada heard the familiar whistle of incoming shells, but instead of the dull thud of impacts against the earth, the air above the ridgeline erupted with a series of sharp, crackling detonations, 70 feet above his bunker's entrance. Then another burst, and another, creating a lethal curtain of steel fragments that rained down through every opening, every ventilation shaft, every entrance to the tunnel system. Within seconds, the screaming began. Men who had felt safe moments before were cut down by shrapnel that fell from above like metallic rain. The fragments found every weakness in the defensive positions, every gap in overhead cover, penetrating spaces that ground bursts could never reach. Yamada pressed himself against the tunnel wall, feeling the hot sting of metal fragments whistle past in the darkness. That morning, as he helped carry wounded men deeper into the tunnel network, Yamada heard something that would stay with him for the rest of his life. One of the junior officers, a man who had studied engineering in Tokyo, was examining a piece of shrapnel that had wounded him. With trembling hands, he spoke words that seemed impossible. "The Americans have made their shells intelligent. They know when to explode without touching anything." This moment of technological revelation would ripple through the Japanese defensive positions on Okinawa, Iwo Jima, and across every remaining Pacific stronghold. The Americans had deployed a weapon that rendered traditional defensive doctrine obsolete. Underground bunkers, carefully prepared fighting positions, elaborate tunnel networks, all the fortifications that Japanese forces had spent months constructing had suddenly become far less protective against an enemy that could rain death from the sky without ever touching the ground. The story of how Japanese defenders came to face this revolutionary weapon began not in the Pacific Islands, but in American laboratories and factories, where in the summer of 1940, a group of scientists were tasked with solving what every military power had accepted as an unsolvable problem. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The National Defense Research Committee, formed on June 27, 1940, brought together leading American physicists and engineers under the direction of Vannevar Bush. Among them was Merle Tuve, a physicist whose brilliant but volatile temperament would eventually lead a team that numbered over 1,000 scientists and engineers working in a converted Chevrolet garage in Silver Spring, Maryland. The problem they faced was devastating in its simplicity. Japanese and German aircraft were destroying Allied ships and ground formations with alarming efficiency. Conventional anti-aircraft guns required either a direct hit against a maneuvering target, traveling at 300 miles per hour, or a timed fuse set to explode at a predetermined altitude based on calculations that were often wildly inaccurate. In practice, at the start of the war, it required roughly 20,000 shells to down a single enemy airplane. Some estimates reached as high as 100,000 rounds per kill. The mathematics were brutal. If a fleet needed to defend itself against a coordinated air attack by 20 aircraft, gunners might need to fire 400,000 rounds, assuming perfect conditions and adequate time. In reality, most attacks came too quickly for such volume, and most ships simply didn't carry enough ammunition. The idea of a proximity fuse had been considered for decades. Create a fuse that could sense when it approached a target and detonate automatically. Simple in theory, impossible in practice given 1930s technology. Germany had investigated proximity fuses as early as 1930, developing more than 30 different designs, including acoustic sensors that would trigger on engine noise and electrostatic detectors that would respond to charged surfaces. By 1939, German researchers had judged the technical hurdles insurmountable. When Adolf Hitler's leadership issued directives in 1940, prioritizing only projects that could reach production within 6 months to support the coming invasion of the Soviet Union, Germany's proximity fuse programs were among the casualties. Rheinmetall-Borsig would resume limited work in 1944, far too late to influence the war's outcome. The British had progressed further. By 1939, researchers at the Telecommunications Research Establishment had conceived of using a small Doppler radar system within a shell. They tested prototypes on rockets, which experienced far less severe acceleration than gun-fired projectiles. But Britain's program faced 2 critical obstacles that proved insurmountable with their available resources. The cost was prohibitive, and Britain's industrial capacity was already stretched to the breaking point, manufacturing aircraft, tanks, and basic munitions. More fundamentally, they could not solve the miniaturization problem. The smallest vacuum tubes available, those used in hearing aids, were still far too delicate to survive the violent acceleration of being fired from a gun. When a 5-inch naval shell is fired, it accelerates from 0 to 2,600 feet per second in roughly 20 feet of gun barrel. This creates an acceleration force of 20,000 times the force of Earth's gravity, what engineers call 20,000 G. To visualize this, imagine taking a delicate glass Christmas ornament and hitting it with a sledgehammer 20,000 times in the span of a fraction of a second. Every component, every wire, every solder joint experiences this crushing force. The shell then spins at 25,000 revolutions per minute as it passes through the rifled barrel, creating centrifugal forces that would tear apart any conventional electronic assembly. And after surviving this violence, the delicate electronics had to function perfectly during the few seconds of flight time before reaching the target, all while exposed to extreme temperatures and the stress of supersonic flight. By 1941, British scientists had working prototypes that functioned perhaps 50% of the time under ideal conditions. For military service, this was inadequate. A weapon that worked half the time was worse than useless. It gave commanders false confidence while consuming resources. The British shared their research through the Detonate mission when America entered the war, a remarkable act of scientific cooperation. But it would be American scientists and, more importantly, American industry that would actually make it work. The Americans took the British research and did what no other nation could. They built it. Not a laboratory curiosity that worked sometimes under perfect conditions, but a mass-produced munition that could be manufactured by the millions and deployed across 2 oceans simultaneously. Tuvey's Section T at what became the Applied Physics Laboratory of Johns Hopkins University, established on March 10, 1942, settled on a radio-based proximity fuse using Doppler radar principles. A miniature transmitter in the nose of the shell would emit radio waves at roughly 180 to 220 megahertz. When these waves struck a target and reflected back, the frequency would shift due to the Doppler effect, the same principle that makes a train whistle change pitch as it passes you. When the reflected signal reached a predetermined frequency, indicating the target was within lethal range, approximately 70 feet, for most applications, an electrical circuit would close and detonate the shell. The theory was elegant. Making it work was another matter entirely. Consider the engineering challenges in their full complexity. The fuse had to fit into the nose of a 5-inch artillery shell, leaving room for 7 pounds of high explosive. Inside this space, roughly the size of a wine bottle, engineers had to fit a complete radio transmitter and receiver, a power source, multiple safety mechanisms to prevent accidental detonation, and a detonator assembly. All of this had to function in temperatures ranging from -40 degrees Fahrenheit in Arctic operations to +120 degrees Fahrenheit in tropical climates. It had to survive storage for months in the humid, salt-laden air of a ship at sea. Most daunting of all, it had to withstand the shock of being fired from a gun and still work perfectly seconds later. James Van Allen, a young physicist who would later become famous for discovering the radiation belts around Earth, joined the Applied Physics Laboratory in April 1942 as a founding member. He faced the task of developing what the team called rugged vacuum tubes, a phrase that seemed almost contradictory. Vacuum tubes, by their nature, were fragile glass envelopes containing delicate wire filaments thinner than human hair. Van Allen started with miniature tubes that Raytheon and Sylvania had developed for hearing aids. These were designed for the gentle environment of sitting in someone's pocket, not the violence of artillery fire. Working with Sylvania Company engineers, Van Allen redesigned the tubes from first principles. The glass envelopes were thickened and carefully annealed through a heating and cooling process that made them less brittle. The internal filaments and grids were redesigned with shorter spans and heavier cross-sections, trading some electrical efficiency for physical durability. The tubes were potted in wax inside the fuse body, which cushioned them against shock like a shock absorber. Every aspect was tested by firing complete fuses from a vertical gun into soft earth at the Naval Proving Grounds in Dahlgren, Virginia. The ground caught the shells gently enough that researchers could recover the fuses and examine the tubes under microscopes to see exactly what had broken and where. Through hundreds of test firings and thousands of design iterations, examining each failure under magnification, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness against Japanese air attacks that were devastating the Pacific Fleet, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during the production ramp-up. They were right. By early 1943, reliability had climbed above 90%. But vacuum tubes were only one challenge among many. The fuse needed a power source capable of delivering enough electricity to power the radio transmitter for the few seconds of flight time. Conventional batteries were too large and had limited shelf life, particularly in tropical heat where chemical reactions accelerated and batteries leaked corrosive acids. Engineers developed a reserve battery that used a liquid electrolyte, kept physically separated from the battery plates until activation. When the shell was fired, centrifugal force from the spinning projectile spun the electrolyte into contact with the plates through carefully designed channels, generating electricity. This gave the batteries indefinite storage life and eliminated the risk of chemical deterioration. The fuse needed multiple safety mechanisms, each one critical to preventing catastrophic accidents. It could not arm until the shell was well clear of the gun, and premature detonation in the barrel would destroy the weapon and kill the crew. It required protection against accidental detonation from radio interference or the ship's own powerful radar systems broadcasting hundreds of kilowatts. It needed wave suppression circuitry to prevent premature detonation when fired at low angles over water, where radio waves reflecting off the ocean's surface could create false triggering signals. Each safety feature added complexity and more components that had to survive the 20,000 G acceleration. By the time development was complete, each proximity fuse contained approximately 130 miniaturized electronic components. The Mark 32 fuse for the Navy's 5-inch gun was 8 inches long and weighed just over 2 pounds. Inside its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942 anywhere in the world. On August 12, 1942, the light cruiser USS Cleveland conducted the first operational test in Chesapeake Bay. The target was 3 radio-controlled drone aircraft flying evasive patterns. Using conventional ammunition, downing these maneuvering drones typically required dozens or even hundreds of shots, with many tests ending without a single hit. Cleveland's gunners, firing proximity-fused shells for the first time in an operational scenario, destroyed all 3 drones with just 4 bursts on the first day of testing. The 4th shell was never fired. There were no more drones available. The test director had not prepared additional targets because conventional anti-aircraft tests never achieved such results. The Navy immediately canceled the remainder of the scheduled tests. There was nothing left to prove. Orders went out for mass production to begin at maximum possible speed. 5 companies were selected to manufacture the fuses: Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Production started slowly, constrained by the need to set up entirely new assembly lines and train workers in techniques that had never been used before. By the end of 1942, factories were producing 500 fuses per day, but American industrial capacity was just warming up. By late 1943, production had reached 40,000 fuses per day. Over the course of the war, American industry would produce more than 22 million proximity fuses at a cost exceeding $1 billion 1940s dollars. equivalent to over $14 billion in today's currency. More than 100 factories participated in some phase of production. The Crosley Corporation in Cincinnati alone produced over 5,913,000 fuses, representing 24% of total production. The company employed 10,000 workers operating continuously 7 days a week, achieving peak output of 16,500 fuses daily. Sylvania Electric Products in Ipswich, Massachusetts, produced even more, manufacturing over 5,683,000 Mark 32 fuses, while also producing 95% of all miniature vacuum tubes used across the entire program. Thousands of workers, many of them women entering industrial work for the first time, assembled the intricate components under conditions of absolute secrecy that rivaled the Manhattan Project. Workers signed secrecy oaths before beginning employment and were searched both entering and leaving the facilities. They did not know what they were building. Supervisors told them only that their work was critical to the war effort and that lives depended on their precision. Security surrounding the proximity fuse was second only to the atomic bomb program. The device was given the deliberately misleading code name VT fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. The very existence of the fuse was classified at the highest levels. Even its use in combat was initially restricted to situations where there was absolutely no chance of a dud falling into enemy hands for examination. The first combat use came on January 5, 1943, off Guadalcanal in the Solomon Islands. 4 Japanese Aichi Type 99 dive bombers attacked a U.S. Navy task force in the early morning darkness. As the aircraft broke off their attack runs and began climbing away, Lieutenant Commander Red Cochran, commanding the aft 5-inch battery on the light cruiser USS Helena, fired 3 salvos of proximity-fused shells at the departing bombers. All 3 shells exploded near one of the aircraft at precisely the calculated distance, shredding it with shrapnel despite never directly hitting the plane. The aircraft's wings separated from the fuselage, and it plunged into the sea with no survivors. Helena's gunners had achieved what would have required dozens or potentially hundreds of conventional shells fired by the most skilled crews. They had downed an enemy aircraft without scoring a direct hit, using only their second salvo. Word of the success spread rapidly through the Pacific Fleet. Though under strict security protocols that limited detailed information, even among senior officers who lacked clearance for the program. By mid-1943, substantial quantities of proximity-fused ammunition were being shipped to Pearl Harbor and forward bases, though always with armed guards and special handling procedures. Combat results exceeded every prediction. In 1943, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuses being used in only 25% of shells fired. The mathematics were stunning. Using 1/4 of the ammunition, proximity fuses achieved 1/2 of the kills, meaning they were approximately 6 to 8 times more effective than conventional ammunition. Admiral Arleigh Burke, who would later serve as Chief of Naval Operations, recalled that when he served as Chief of Staff to Admiral Mark Mitcher, commanding the fast carrier task forces that struck deep into Japanese-controlled waters, proximity fuses knocked down enemy planes by the dozens during attacks that would have otherwise overwhelmed the fleet's defenses. The true effectiveness was demonstrated in a single action on May 11, 1945, off Okinawa during Operation Kikusui No. 6. 2 destroyers, USS Hadley and USS Hugh W. Hadley, came under assault from approximately 150 Japanese aircraft during an attack that lasted approximately 1 hour and 25 minutes. Many of the aircraft were loaded with explosives and flown by pilots intent on suicide, runs the kamikazes that had become Japan's most desperate weapon. During this intense combat, the 2 destroyers and 4 supporting craft faced overwhelming odds. Hadley's gunners knocked down 23 enemy planes using proximity-fused ammunition before being hit by 1 bomb, 3 kamikaze aircraft, and 1 Oka rocket bomb, an attack that would have sunk most vessels. Hugh W. Hadley accounted for additional aircraft before being struck 4 times by suicide planes and left dead in the water. Both ships survived despite catastrophic damage that left them floating wrecks. The verdict on proximity-fused ammunition in this action was unequivocal, indispensable. Without the fuses, intelligence analysts estimated, both destroyers would have been sunk in the opening minutes of the attack, along with most of their escorting vessels. But for most of the war, the Pentagon strictly forbade use of the fuse over land. The risk was too great that a dud shell would fall into enemy hands, where German or Japanese engineers might reverse engineer the technology or develop countermeasures. If Germany equipped its anti-aircraft guns with proximity fuses, intelligence analysts estimated Allied bomber losses could increase by 300% or more. The strategic air campaign against German industry might become impossible to sustain, so the fuses were used only over water, where dud shells would sink beyond enemy reach into the ocean depths. When a dud proximity-fused shell landed on Sicily during the invasion in July 1943, headquarters dispatched a special recovery patrol to locate and secure it before German forces could find it. The shell was recovered, and the incident led to even stricter protocols. This absolute security restriction began to crack in June 1944 when Germany unleashed the Von flying bomb against London. Launched from sites across the English Channel, the pilotless missiles approached at speeds of 400 miles per hour, faster than many Allied fighters and small enough to be difficult targets. From June to late August 1944, Germany launched over 9,000 V-1s against Britain, an average of 120 per day. The pilotless missiles inflicted tens of thousands of civilian casualties and created a crisis atmosphere in London, as families slept in subway stations and government officials debated evacuation plans. British defences initially could destroy only 17% of the V-1s that entered the coastal gun belt. The situation was desperate enough that Prime Minister Winston Churchill personally authorised use of proximity fuses in anti-aircraft guns, defending Britain, overriding security concerns because the immediate threat outweighed the risk of German capture and analysis. Fuses were rushed into production, specifically calibrated for the small, fast Von profiles. British and American anti-aircraft guns along the coast were equipped with proximity-fused ammunition, working in conjunction with new radar systems and the latest fire control computers. The effect was dramatic beyond all expectations. Within 4 weeks, the destruction rate climbed to 74%. During one day in late August, 82% of incoming V-1s were shot down, creating such a wall of explosions over the English coast that German launch crews began to question whether their missions served any purpose. Churchill later stated that the proximity fuse had made possible the successes that Anti-Aircraft Command was obtaining against what had seemed an unstoppable weapon. The Von campaign demonstrated beyond doubt that the proximity fuse was war-winning technology, but it also meant the secret was partially compromised. Thousands of fuses were being fired over land where duds could be recovered. The risk that had seemed so unacceptable in 1943 now had to be weighed against military necessity as the war entered its final phase. In the Pacific theater, this calculation was about to change completely. Japanese defensive doctrine had evolved throughout the war in response to overwhelming American firepower. On islands like Tarawa and Peleliu, Japanese forces had learned that defending beaches against American amphibious assaults was futile. American naval gunfire could simply obliterate any fortifications within sight of the ocean. The new doctrine, perfected by General Tadamichi Kuribayashi on Iwo Jima and Lieutenant General Mitsuru Ushijima on Okinawa, emphasized defense in depth using underground fortifications. Japanese engineers spent months, sometimes years, carving elaborate tunnel networks deep into volcanic rock and coral limestone. These underground fortresses featured multiple levels connected by passages, with command posts, barracks, ammunition storage, and hospitals all protected by dozens of feet of solid rock. On Iwo Jima, Japanese engineers carved 11 miles of tunnels before the American invasion began. Pillboxes and gun positions were built with reinforced concrete walls 4 feet thick, capable of withstanding direct hits from battleship shells. Fighting positions were carefully camouflaged and mutually supporting, designed so that clearing one position would not eliminate the threat from adjacent positions connected by tunnels. On Okinawa, the defenses were even more elaborate. Lieutenant General Ushijima's 32nd Army spent months fortifying the southern portion of the island with a dense network of caves, bunkers, and tunnels carved into the limestone ridges. Every hill became a fortress, The Shuri Castle defense line included interconnected positions that allowed Japanese forces to reinforce threatened sectors through underground passages, appearing to regenerate even after American forces believed positions had been cleared. The effectiveness of these underground defenses had been proven in blood. On Iwo Jima, American intelligence estimated the island would fall in 1 week. Instead, the battle raged for 5 weeks and cost the lives of 6,821 Americans, with another 19,217 wounded, more American casualties than Japanese defenders on the island. Nearly every one of the 20,000 Japanese defenders fought to the death in the tunnel networks. This defensive doctrine was built on a simple principle: American firepower, no matter how intense, could not reach defenders deep underground. Battleship shells, aerial bombs, and artillery fire all expended most of their energy on the surface. Troops in deep bunkers and tunnels were safe from everything except flamethrowers and direct assault by infantry, which meant costly close-quarters fighting that favored the defenders. Japanese commanders had calculated correctly, but only for conventional munitions. They had not anticipated proximity fuses. The restrictions on using proximity fuses over land began to lift in early 1945. The success against Vone flying bombs over England had demonstrated their value, and by this point in the war, thousands of fuses had been expended where duds could potentially be recovered. The secret, while still classified, had been partially compromised. Military necessity now outweighed security concerns. More importantly, American commanders in the Pacific faced a brutal reality. The campaign to take Iwo Jima had demonstrated that Japanese underground defenses could absorb punishment that would have destroyed any above-ground fortification. The upcoming invasion of Okinawa, only 350 miles from mainland Japan, promised to be even more costly. Intelligence indicated the Japanese had spent 8 months fortifying the island with even more elaborate defenses than Iwo Jima. American artillery doctrine needed an answer. Conventional high-explosive shells detonating on the ground created craters and destroyed surface structures, but they provided poor coverage against dispersed troops and were nearly useless against entrenchments. The fragments from a ground burst traveled in predictable patterns, mostly upward and outward in a cone shape. Troops in foxholes, behind walls, or inside bunkers were largely protected. Proximity fuses changed the geometry of destruction. By detonating 70 feet above the target, the fragments spread downward in a killing radius that covered far more area than a ground burst. More critically, the fragments fell from above, finding every opening, every gap in overhead cover, every ventilation shaft. Fortifications designed to protect against ground bursts suddenly became far less effective. The first large-scale use of proximity-fused artillery in the Pacific Ground Campaign came during the final phases of the battle for Okinawa in May and June 1945. By this point, American forces had been grinding through Japanese defensive positions for nearly 2 months. The Japanese 32nd Army, commanded by Lieutenant General Mitsuru Ushijima, had retreated to the final defensive line around Shuri Castle and the southern tip of the island. The fighting had become a methodical, bloody process of reducing fortified positions one at a time. Each cave, each bunker, each tunnel entrance had to be cleared individually. Flamethrowers, demolition charges, and direct fire from tanks eliminated positions slowly at terrible cost. American casualties mounted into the tens of thousands. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Artillery commanders began receiving shipments of proximity-fused ammunition with specific instructions for employment against fortified positions. The technique was different from anti-aircraft use. Rather than setting the fuse for 70 feet, artillery forward observers called for air bursts at varying heights, depending on terrain and target type. For Japanese troops in open fighting positions on ridgelines, shells were set to burst at 60 to 80 feet, creating a lethal rain of fragments over wide areas. For troops in shallow trenches or behind low walls, bursts at 40 to 50 feet provided optimal coverage. Even against cave entrances and tunnel systems, air bursts proved effective by showering fragments into openings and suppressing the troops attempting to emerge. The psychological effect was immediate and devastating. Japanese soldiers who had felt secure in their fortifications suddenly found themselves vulnerable to artillery that seemed to reach everywhere. The constant threat from above created a sense of helplessness unknown in previous campaigns. One Japanese soldier, Corporal Yoshihiro Minamoto, was captured on June 8, 1945, near the village of Yuza on southern Okinawa. During interrogation by American intelligence officers, he provided an account that was circulated through multiple command levels because of its insight into Japanese morale. Minamoto described how proximity-fused artillery had changed the nature of the battle. His unit, part of the Japanese 24th Division, had withstood weeks of conventional bombardment in fortified positions without severe casualties. The concrete and earth overhead protected them. Men could rest between engagements and maintain their fighting strength. When the American artillery began using airbursts, everything changed. Minamoto described hearing the shells explode overhead with a different sound, sharper, more concentrated. Then came the rain of metal fragments finding every gap, every opening in their positions. Men who moments before had been safe were suddenly wounded or dead. He recounted watching soldiers refuse to leave cover even when ordered to man defensive positions. The fear of the bombardment from above broke the discipline that had kept the unit cohesive through 2 months of combat. By the time of his capture, Minamoto said, his company had been reduced to less than 30% strength, with most casualties coming from artillery rather than direct assault. American intelligence officers compiled reports from multiple prisoners regarding proximity fuses. The consistent theme was surprise and helplessness. One Japanese artillery officer, captured on June 20th, provided technical analysis. He explained that Japanese defensive doctrine had been built around protection from ground bursts. The overhead cover on fortifications was calculated to stop fragments traveling in upward trajectories from ground explosions. Air bursts reversed the geometry. Fragments now traveled downward, finding weaknesses in overhead protection. The officer noted that reconstructing every defensive position to provide adequate overhead protection would require months of work and vast quantities of materials that Japan no longer possessed. The statistical effect of proximity fuses in ground combat was significant, though less dramatic than their impact against aircraft. Analysis conducted after the battle indicated that proximity-fused artillery achieved approximately 3 times the casualty effect per shell compared to conventional impact fuses when targeting troops in field fortifications. This multiplication factor meant that artillery fire missions could be significantly shorter while achieving the same suppressive effect. This preserved ammunition allowed artillery to shift fires more quickly between targets and reduced the time Japanese troops had to seek cover or evacuate threatened positions. The tactical implications were profound. American infantry advancing on Japanese positions could rely on more effective preparatory fires. The confidence that artillery could suppress defensive positions, even when the exact location wasn't known, changed how attacks were planned. Artillery could now blanket suspected enemy areas with airbursts, making it extremely hazardous for Japanese troops to remain in positions that had previously seemed secure. On Okinawa, during the final American offensive against the last Japanese defensive positions in late June 1945, proximity-fused artillery fired more than 80,000 rounds. This represented approximately 40% of all heavy artillery ammunition expended during those final weeks. The concentration was, intentional artillery commanders had learned that the fuses were most effective when used in sustained barrages rather than individual fire missions. The effect on Japanese defensive operations was cumulative. Unlike conventional artillery, which troops learned to endure by taking cover during barrages, proximity-fused fire provided no safe refuge. The constant threat from above created psychological stress that accumulated over days and weeks. Japanese soldiers in the final defensive positions faced not just death, but death that could strike without warning from above, against which their elaborate fortifications provided little protection. Lieutenant General Ushijima, the Japanese commander on Okinawa, committed ritual suicide on June 23 as American forces overran his final headquarters. His final messages to Tokyo made no specific mention of proximity fuses, but they described American artillery as far more effective than anticipated and noted that defensive positions proved inadequate against new American bombardment techniques. For Japanese military planners, observing the battle from the homeland, the implications were terrifying. If American forces invaded the Japanese home islands which everyone expected by late 1945, the underground fortifications being prepared to defend the beaches and cities would face the same vulnerability. The defensive strategy that had made Iwo Jima and Okinawa so costly for American forces, trading time and American lives for Japanese determination, would be far less effective against an enemy that could reach into every prepared position with artillery fire from above. The defensive plans for the home islands, developed under the codename Operation Ketsugo, relied on the same principles that had worked on Iwo Jima and Okinawa: extensive underground fortifications, layered defensive zones, and acceptance of total casualties in exchange for inflicting maximum losses on the invaders. Proximity fuses threatened to undermine this entire strategy. Beyond the physical destruction, the psychological impact on Japanese forces in the closing months of the war was significant. The fuses represented yet another technological advantage that demonstrated American industrial and scientific superiority. For soldiers who had been told that Japanese spirit and determination would overcome American material advantages, each encounter with proximity-fused artillery reinforced the growing realization that the war was lost. This realization manifested in subtle but important ways. The number of Japanese soldiers surrendering increased dramatically in the final months of the war, particularly on Okinawa. During the battle, 11,250 Japanese military personnel surrendered, representing 12% of the force deployed. This was an unprecedented percentage for Japanese forces, far higher than on any previous Pacific battlefield. While multiple factors contributed to this increased declining morale, recognition of inevitable defeat, exhaustion, and starvation interrogation, reports consistently mentioned proximity-fused artillery as a factor in the decision to surrender. The weapon removed the last advantage Japanese forces possessed: the ability to survive through superior defensive positions and endurance of bombardment. American commanders recognized the weapon's value, but also its limitations. Proximity fuses were expensive. Each fuse cost $18–19–45, equivalent to roughly $250 today. In an artillery battle that might consume thousands of shells, this represented significant expenditure. Conventional high-explosive shells remained more economical for many fire missions, particularly against structures or vehicles where ground bursts were as effective as air bursts. The fuses also required specific handling procedures. They could not be stored in extremely hot conditions because the batteries would deteriorate. They required careful inventory management because each fuse had a shelf life measured in months, not years. Forward artillery units needed personnel trained in the proper loading and handling procedures to prevent accidents or malfunctions. Despite these limitations, by late 1945, proximity fuses had become standard ammunition for American artillery in the Pacific. Production had reached such levels that supply was no longer a constraint. Every artillery battery had ready access to proximity-fused ammunition for missions where air bursts provided advantage over conventional shells. The rapid expansion of proximity fuse usage in the Pacific during 1945 represented one of the fastest deployments of a new weapons technology in military history. From restricted use only over water in 1943 to unrestricted employment across all Pacific combat zones by mid-1945 took less than 30 months. This acceleration reflected both the weapon's proven effectiveness and the increasing desperation of the final campaigns against Japan. For the Japanese forces that encountered proximity fuses, the weapon represented something beyond its immediate tactical effect. It symbolized the fundamental imbalance in the war. American industry could develop, test, and mass-produce sophisticated electronic devices by the millions, while Japanese industry struggled to produce basic munitions and spare parts for existing equipment. Japanese engineers, when they eventually examined captured proximity fuses after the war, expressed professional admiration mixed with recognition of how completely outmatched Japanese industrial capacity had been. The miniature vacuum tubes alone represented manufacturing capabilities Japan did not possess. The precision required to assemble 130 components into a package that could survive artillery launch exceeded Japanese production standards for any mass-produced item. 1. Japanese engineer, interviewed by American technical intelligence teams in October 1945, described examining a proximity fuse with a sense of unreality. The device contained more sophisticated electronics than many Japanese aircraft instruments. yet the Americans had produced 22 million of them. He calculated that at Japanese production rates and costs, manufacturing even 1 million such devices would have consumed more than 20% of Japanese electronics production capacity for an entire year. This recognition of industrial disparity cut deeper than battlefield defeats. It suggested that Japanese defeat had been inevitable, not because of tactical or strategic errors, but because the nation simply lacked the industrial base to compete with American production. The proximity fuse, like so many other American weapons, was less about brilliant innovation than about the ability to transform innovation into mass production. The end of the war in August 1945 came before proximity fuses could be deployed in the massive quantities American planners had envisioned for the invasion of Japan. Stockpiles of proximity-fused ammunition had been building in forward areas throughout the summer. Artillery units were receiving training on optimal employment against the types of fortifications expected on the Japanese home islands. Had the invasion occurred as planned in November 1945, American artillery would have employed proximity fuses on an unprecedented scale. Plans called for initial bombardments using exclusively proximity-fused ammunition to neutralize Japanese defensive positions before the first landing craft reached the beaches. The intention was to create a curtain of steel fragments falling from above that would make it impossible for defenders to man their positions. The atomic bombs dropped on Hiroshima on August 6th and Nagasaki on August 9th ended the war before these plans could be implemented. The proximity fuse, which had played such a critical role in naval actions and in the final Pacific ground campaigns, was never employed in the massive scale envisioned for Operation Downfall, the invasion of Japan. In the final accounting, proximity fuses fired in ground combat in the Pacific numbered in the hundreds of thousands rather than the millions used in anti-aircraft roles, but their psychological and tactical impact exceeded their numbers. Japanese defenders who had felt secure in elaborate fortifications discovered that American technology had found a way to reach them even in their deepest positions. The weapon changed how both sides thought about defensive warfare. For American forces, it provided a tool that reduced casualties by allowing artillery to suppress enemy positions more effectively before infantry had to assault them. For Japanese forces, it removed the advantage of fortifications that had been so costly for Americans to overcome on islands like Iwo Jima. After the war, as proximity fuse technology was declassified and published in technical journals, military engineers around the world recognized that defensive doctrine would need to change. The fortifications that had dominated military thinking since World War I, trenches, bunkers, underground positions, were now vulnerable to attack from above in ways they had never been before. The legacy of the proximity fuse extended far beyond World War II. Every modern military incorporated the lessons of airburst artillery into their tactical doctrine. Defensive positions needed overhead cover designed not just to stop fragments traveling upward from ground explosions, but to withstand the downward rain of fragments from airbursts. The technology itself continued to evolve. Post-war proximity fuses used transistors instead of vacuum tubes, making them smaller, more reliable, and capable of surviving even greater acceleration forces. Modern proximity fuses can distinguish between different types of targets, adjust their detonation height automatically, and even resist electronic countermeasures. But the fundamental principle remained unchanged. Detonate the weapon at precisely the right distance from the target to maximize effect. This simple concept, so difficult to achieve with 1940s technology, became the foundation for generations of weapons systems. The story of proximity fuses in the Pacific demonstrates how technology, production capacity, and tactical innovation combine to change warfare. The fuses themselves were remarkable achievements of engineering and miniaturization. The ability to produce 22 million of them was an achievement of industrial organization and manufacturing capability. The tactical employment that made them so effective was an achievement of military adaptation and learning. For the Japanese soldiers who faced proximity-fused artillery in the final battles of the war, these abstract achievements translated into concrete reality. The sound of shells exploding overhead, the rain of fragments finding every gap in their fortifications, and the growing realization that their defensive positions could no longer protect them from an enemy that possessed such overwhelming technological advantage. Sergeant Takeshi Yamada, The Japanese soldier who experienced proximity-fused artillery in northern Okinawa on April 27th survived the battle and was among those who surrendered in late June. During his interrogation, American intelligence officers asked him what convinced him to surrender rather than fight to the death as his training demanded. His answer was recorded in the interrogation report. The shells that exploded in the air. We had no defense against them. Our positions, which we had worked for months to build, became death traps. When the American artillery started using those shells, I knew we could not win. I knew Japan could not win. We were fighting an enemy who could make the impossible possible. This recognition that American forces possessed technology that seemed beyond Japanese capability to match or counter appeared repeatedly in prisoner interrogation reports from the final months of the war. The proximity fuse was not unique in this regard. Radar, advanced fire control systems, nuclear weapons, and many other American technologies demonstrated similar advantages. But the proximity fuse had a particular psychological impact because it affected the most basic element of warfare, the ability to survive on the battlefield. Soldiers could accept that the enemy had better aircraft or ships or radar. These were distant, strategic advantages. But when the enemy possessed artillery that could kill you, even in fortifications designed specifically to protect against artillery, this touched on something more fundamental. It suggested that the war had been not just lost, but lost in ways that Japanese forces could never have prevented. Superior courage, better training, stronger determination. None of these traditional military virtues mattered when the enemy possessed the industrial capacity to produce millions of sophisticated weapons that gave them decisive advantages in every engagement. This understanding, spreading through Japanese forces in the final months of the war, contributed to the collapse of resistance that occurred with surprising rapidity after Japan's surrender. The expectation had been that Japanese forces, particularly in China and the Pacific Islands, would continue fighting even after the government surrendered. Instead, most Japanese units laid down their arms with minimal resistance. The proximity fuse had played a small but significant role in creating the psychological conditions for this acceptance of defeat. It was yet another piece of evidence that continuing the war would achieve nothing except additional casualties against an enemy whose technological and industrial advantages made Japanese victory impossible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.